In this video, I'm going to show you the image of why we need a peak detector in receivers of SDRDES. Before talking about the peak detector, let's review the clock data recovery CDR at the receiver one more time. Let's start with the single VCO PO based CDR image as an example, which may eliminate the mismatch, frequency pooling, and area issues. In addition, the dual loop can still have the frequency tracking loop to avoid the false lock, and the phase tracking loop will still be phase aligned with the input data. But if someone disconnected, pull out the cable, or something like that, what happened? Yes, the input data went away. Then what happened? Correct. The input data DIN will be at a noisy level, and the CDR is ideally entering an open loop. Can you think about how the CDR was trying to lock the input noise in an open loop image for 5 seconds? Correct. Ideally, if the input noise is a normal distribution with a zero mean, the phase detector output would provide early and late equally in a period of time. Therefore, the CDR is in tri-state, and the VCO frequency or phase should stay the same or not move that much as before while the input data was present. Is that true? Think about the charge pump current mismatch images for 5 seconds. Bingo! In a real charge pump circuit, the up and down current will have a current mismatch, no matter if it's big or small, but it should be there. Therefore, in a long term, the mismatch current, which could be up or down, will drive the VCO faster, slower, and vice versa, even though both up and down counts are the same in the tri-state. So what can we do? Can you look at the lock detector images for 5 seconds? Right. The role of the lock detector is not only to detect if the CDR or VCO is down in the frequency tracking mode and guide the CDR to the phase tracking mode, but it can also help detect if the VCO frequency was drifting up or down too much out of the specified turbo range. Therefore, if the data went away, then the lock detector will prevent the CDR clock frequency or phase out of control by detecting the frequency error and then pull the CDR back to frequency acquisition mode, back to the reference clock. Is that good enough? Think about the response time images of the lock detector in 5 seconds. Correct. The lock detector could be a counter-based comparator by comparing both counts of the divided VCO cycles and the reference clock cycles. Therefore, the lock detector would take time to make a decision at a certain cycle counts, which is the delay or response time. Unfortunately, the lock detector could be too slow to detect or catch the frequency drift in a timely manner. So the CDR clock frequency could either drift up or down too much to malfunction the whole receiver. Alright, what should we avoid it? Think about the input data monitor images for 5 seconds. Very good. If we have any data detection circuitry to monitor for loss of the signal event, that would be a good warning flag to notify the CDR as soon as possible. For example, if there is no data detected, the loss of the signal flag will switch the CDR back to frequency acquisition mode to avoid the frequency drifting too much quickly, to avoid any timing variation at the digital blocks. if the recovery clock frequency drifts too fast, or any stop clock events if the recovery clock frequency drifts too slow, and then to power down the clock. If the loss of a signal detector is handy, can you think about the circuit images for 5 seconds? Nice, the PCS error monitor could be used to serve the loss of a signal detector in digital. But the latency could still be an issue as well, and the response time could be too slow to stop the CDR frequency drift in time. To make sure a fast response, the analog peak detector would be needed to serve the loss of a signal detector. Therefore, to serve the SDRDES ecosystem between different vendors, most protocol committee defines the peak detector demands in the standard of PCIe Gen 1 to Gen 5, SATA, USB, etc. Alright, can you think about the requirements of the peak detector specification in those SDRDES protocol? Bingo! To detect the loss of a signal, we must define the input swing level as a threshold. Taking the PCIe as an example, the low threshold is 65 mV, and the high threshold is 175 mV. So, below 65 mV is considered noise, and above 175 mV is to be considered a very input signal level. Also, the data rate will be another obvious factor for the signal detection condition. To relax the design challenge, the data rate will mostly not require full rate under such low input swing, and that's in the 500 MHz clock pattern to 2.5 gigabit per second PRBS7 pattern range. What else could be the target? Think about the response time images for 5 seconds. Right. Usually, the response time requirement will be a few nanoseconds or a few clock periods specified in different protocols. After understanding most of the specification, could you think about the circuit image of the peak detector in 5 seconds? Excellent. The most critical one would be the rectifier or envelope detector, which will convert the input AC signal to the output DC signal. Again, the envelope detector is very similar to the RF circuit direct down conversion topology. So I draw a mixer with a low pass filter to get a DC content. After that, what should we add to the following stage? Perfect. We should convert the analog signal to a digital signal as an interrupting flag in digital. Therefore, an analog to digital converter ADC is a must. How about the input sensitivity, since we might need to detect the input signal as low as 50 mV? Correct. We should add an amplifier before the envelope detector, such that the input sensitivity can be as high as possible, down to 50 mV. But in some specifications, the low threshold is 100 mV. Below 100 mV is considered noise and should not be considered a valid input signal level. So we need to decrease the input sensitivity up to 100 mV by either degenerating the preamplifier gain or the output DC of the envelope detector. Here are a summarized image of why we need a peak detector in receivers of SDRDES. In a real application, the input data will go away even after a stable link transmission. Either the counter-based lock detector was not fast enough, or the PCS error monitor could have too much latency. Both blocks are not suitable for loss of signal detection, which must be as fast as possible to avoid the VCO or CDR frequency drifting too much. Therefore, if we cannot maintain the CDR's clock stably while the input data went away, the link might be either getting error transmission or shutting down the whole clocking system. Hopefully, an analog peak detector may detect within a fast enough response time as a loss of signal detector. Most of the protocols even recognize it's handy in the SDRDES system, and then put it into the electrical specifications of the input threshold swing, data rate pattern, and response time. From those requirements, the circuit images of a typical peak detector may even include a preamplifier for an input sensitivity improvement, in addition to the envelope detector. To tolerate different sensitivity, range control or adjustment might be needed. Lastly, the ADC is a must as an interface between the analog front end and digital code. Hopefully, this circuit image will explain to you why the peak detector is so handy in every multiple SDRDES. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.